All right, so let's see how you guys did. The fun thing about working with hyperbolic functions and finding the derivatives, we can approach it two different ways. Either we can switch all the hyperbolic functions in terms of sine and cosine and then substitute in the exponential function and then take the derivative. Or we can take the derivative first and then do any kind of simplifying that we may need to do. So I'll show you guys both ways just so you can get a flavor of what's going on and if you guys want to use it. So here's your solutions. So this first one, if we wanted to take the derivative, it's a product. So one way we could do it is we could use the product rule. Okay, so we could do derivative of our first function times the second function plus derivative of the second function times the first function. All right, so something like this. Okay, and then cleaning that up, we could factor out an e to the x. Something like that. And then just because we have this e to the x here, I'm curious to see what would happen if we use the exponential form of our hyperbolic functions. Okay, and some nice things work out. We have our same denominator, so we can add up these fractions. So the top would become e to the x plus e to the x is 2e to the x. And then e negative x minus e negative x is 0. Okay, so something like that. 2's cancel. E to the x times e to the x is just e. Let's see, when we multiply, we add up the exponents. So it'll be e to the 2x. So all of that for e to the 2x. It's kind of fun, right? Alternatively, so I'll switch colors for this one, or f prime of x oops, sorry, let me back up. Okay, so the hyperbolic cosine, we would substitute that first. Okay, so this is still, dang it, it's not the derivative. There we go. It's just the normal function. And then the hyperbolic sine, we would write in the exponential definition. Okay, and then we can, wait, what am I doing? Oh, goodness gracious, guys. I'm so sorry. Let's go all the way up. This is what I'm trying to mimic. So it's just this first one I'm talking about. I was referencing myself. So I'm going back to the original. That's what I meant, right? Okay, and then we distribute that e to the x. So again, x plus x is 2x. And then that's the 2x. And we multiply e to the x times e to the negative x. That's like multiplying reciprocals. So you're just going to get 1 over 2. And then when you take the derivative of that, you can bring that 2 out to the front and worry about it at the end. Okay, because that's how constants work with the derivatives. And now f prime of x is equal to 1/2. And now when we take the derivative of e to the 2x, it's the chain rule. Let's take the derivative of the outside function first times the derivative of the inside function. Derivative of 2x is 2. And then the derivative of the plus 1 is just 0. All right, and then clean it up. 1/2 times 2 cancels to 1. So again, we just have e to the 2x. Okay, so notice we're getting the same derivative. It's just a different approach. All right, let's look at solution number 2. Again, kind of the same thing. We can choose to do the quotient rule right off the bat. Or we can change to the exponentials versions of everything. But I'm just gonna go for the quotient rule on this one. All right, and then why this one's a little bit different than number one. Number one had an e to the x in the original formula, right? So that's kind of what clued me, and maybe I should write the hyperbolic function in terms of the exponential e to the x. So that was my thought process. But here, we don't have an e to the x anywhere. So that's why I'm thinking, let's just go for it. Let's just use the quotient rule. All right, so the quotient rule tells us to take the derivative of the top function first. So the derivative of this would be 0 plus hyperbolic cosine times the bottom function minus the derivative of the bottom function. So that'd be negative, like that, times the top, all over the bottom squared. Okay, so let's simplify. Switch colors to simplify. All right, and then minus minus becomes plus. Okay, what can cancel? Let's see, those cancel. And then we have cosh, which is two coches. So that's how the top cancels. And then on the bottom, we have this. I mean, I'm sure we can do more with this, right? We could put it into the exponential function and see if anything comes out of this. You know, but I'm fine with this. So we'll just say that is our final answer. All right, and then finally we have one more. All right, so again, that's the derivative. Okay, and we have one more derivative we're going to take, and that's number 3. And this was the original function, hyperbolic sine of the natural log of x. Okay, and then this looks like a chain rule. So I'm just going to hop in with the chain rule, and then we can do another, alternative too. But let's start with the chain rule. So first, that means we would take the derivative of the outside function times the derivative of the inside function. Okay, something like that. And then let's keep going because this doesn't look that pretty. We know the hyperbolic cosine, well, you can write that out in terms of the exponential function. All right, it's e to the input plus e to the negative input, and the input in this case is the natural log of x. Okay, so we can expand out that definition, and I did that because up here in this example, the argument is just t, fairly straightforward. This argument is messy. So that's why I took it to this additional step. Also, natural log, we're thinking e exponential. So if we're seeing natural logs, if we're seeing e's in our equation, that relates to the exponential definition of these hyperbolic functions. So again, that's our strategy. That's my thinking process. That's why I'm taking it to the definition using those exponentials. And then all of this nice stuff happens. We can think of it like canceling. It's not exactly like canceling. And then let's bring this into the exponent so we can cancel it. Okay, so this is going to be x plus 1 over x over 2 times 1 over x. All right, and then let's see. We don't like fractions within fractions, so I'm going to combine the denominators. So the bottom's going to be just 2x, and then we'll multiply 1, 2, 3 terms by x to clear the denominator, okay, to get rid of that improper fraction. So we're going to multiply top and bottom by x, and so we're looking at x squared plus 1 divided by 2x squared. Okay, and there you go. So that's our derivative. Let me show you an alternative way of looking at it, just so you know we have some options when we're dealing with our hyperbolic function. So remember, this is where we started. This was the original problem. Right off the bat, we could have used the exponential definition of the hyperbolic sine and then take the derivative. All right, so first we took the derivative and then used the definition. In this direction, we're using the definition, then taking the derivative. Okay, so let's see. Again, this is going to cancel. So it's x minus, again, I can bring that into the exponent. All right, and then the benefit is that this is a little bit more straightforward to take the derivative of, don't you think? So if we wanted to take y prime, the derivative of x is 1. This, we're going to bring down negative 1. Minus minus becomes plus. And then subtract 1 from the exponent. And so we're looking at 1/2 times 1 plus 1 over x squared. And if we wanted to, we can make it, let's make it look like our previous answer. So let's distribute that 1/2. Just distributing the 1/2, and then we can make a common denominator by adding an x squared. And so we're looking at x squared plus 1 over 2x squared. Right? And that's what we got last time. So different ways of approaching the same problem.